Hey everyone, welcome back. So the next talk is from Jean-Michel Marin. So Jean-Michel is the head of the mathematics department of the University of Montpellier. He has co-authored numerous works on Bayesian statistics, Monte Carlo methods, application to population genetics, and he is also an expert on ABC, Approximate Bayesian Computation. So we'll talk about how ABC could benefit from the back-bias theory. Jean-Michel.
A big challenge. Thank you, Benjamin, for this very nice introduction, and thank you, Pascal and Francis, also for the invitation. It's a real pleasure to be here and to try to make some connection between some methodological and applied works and the world of back-Bayesian works. So I'm supposed to be an expert in approximate Bayesian computation techniques, and I will try today to explain to you how it works and how this method can take benefit from back-Bayesian worlds. So this is a joint works with some numerous colleagues who participate to part of these works. This is the case of Pierre Pudlot from Marseille, of Louis Reynal, which is a PhD of mine, Arnaud Estoup, which is a molecular ecologist in Montpellier, and I take a lot of benefit to discuss with biologists and molecular ecologists because they are very clever and use statistics better than us, even. And also Christian Robert, which is a professor at Paris Dauphine and also at Warwick. I think about Judith, Natesh Pillai, and Judith Rousseau who also contribute to some part of this work. So thank of all these colleagues for working with me. So I will consider the Bayesian paradigm, and I will consider the case where the likelihood function is expensive or impossible to calculate. So I am in the intractable likelihood paradigm. And in that case, it is extremely difficult to sample from the posterior distribution. The posterior distribution is the standard Bayesian, is a product of the prior multiplied by the likelihood, and I cannot evaluate this likelihood, so it's extremely difficult to get some simulation or to get some Bayesian estimate because I do not have access to the posterior distribution. There is two typical situations in which this is the case. The first one is the intractability is due to the presence of latent variable. You have a big latent variable which live in a very large space, and you are not able to integrate this latent variable, which is called U in this slide. This is typically the case in some population genetics application, population genetics model, and the typical models in this field is the coalescence process, and for the coalescence process we only observe the end of the tree, and you have to integrate it out all over the tree, and it's a very big space, and it's almost impossible to integrate this latent variable, and so the likelihood is intractable. In such a situation, there is a lot of statistical methodology who can be applied, the EM algorithm, the keep sampling, some pseudo-marginal MCMC methods, variational approximation, but in some case, and for some specific model, all this type of approximation fail to give good results, and ABC is an alternative. The other situation is when the normalizing constant of the likelihood itself is intractable. So there is no latent variable in this case, but the normalizing constant of the likelihood is intractable. This is typically the case for Markov random field, for instance. And in such a case, we have also some typical pseudo-marginal MCMC method approximation and algorithms which are designed to avoid this normalizing constant problem. Typical, this is MCMC algorithm where you plug within the calculation of the acceptance rate and a bias estimator to avoid this intractability of the normalizing constant, and there is also in this case a lot of variational approximation. So, once again, I will concentrate on this part, this latent variable, but I will introduce an alternative to all this method to deal with the intractability of the likelihood. Here, ABC is a technique that only requires being able to sample from the likelihood, so you only need to be able to sample from the likelihood, and These techniques come from the population genetics community and since about 15 years, and population geneticists still significantly contribute to the methodological development of the method. And with question and other, we worked a lot with population genetics people, and if we work on this ABC, we have to be very grateful to our biologist colleagues, because the first time they introduced as a method, we was very skeptical about the possibility, but at the end, 10 years after, we see, okay, it can work, it can give good results. So I will introduce some methodological aspect of ABC. Our ABC random forest proposal here, and I will discuss possible connection between ABC and PAC-BICE. I will try to say something interesting in the last part. I am not very sure to say something very clever, but let's see. We can discuss about that. Okay, let's start with the methodological aspect of ABC and the first algorithm, which is a likelihood-free rejection sampler. This is an extremely simple algorithm. You have a proper prior distribution, so you generate a parameter value from the prior, you generate a pseudo-observation coming from the model for the corresponding parameter value, and you compare this pseudo-observation to the observed using summary statistics coded by the function eta and a distance d, and if this distance is small enough, according to a threshold which is called epsilon, you say that the corresponding theta value is approximately distributed from the posterior distribution. So it's a very simple and intuitive algorithm which consists to simulate pseudo data, compare to the observed, and see if the two are close enough. Okay. There is, within this algorithm, there is right now three types of approximation. And the first approximation is a standard one. You have an accept-reject algorithm, so you have the first Monte Carlo standard approximation. Okay. You have a second one, which is that this summarization process, it's very difficult to use some sufficient statistics, so you have a loss of information within this summarization step. And the last and third type of approximation using this algorithm is that epsilon is not equal to 0. If epsilon is equal to 0 and if it's a true distance, the theta comes exactly from the posterior if the summary statistic is sufficient, but epsilon equal to 0 is almost impossible. It takes too much time, or it's with probability 0 for continuous variable. So you have the third approximation which corresponds to this epsilon things. Okay, so this epsilon reflects the tension between computability and accuracy. If epsilon tends to infinity, you get simulation from the prior. If epsilon tends to 0, we get simulation from the posterior. And here is the ABC target distribution, where the set A, capital A, is the acceptance set for the seed.
Yeah, sorry. I just had a question on the previous slide. So you're implicitly assuming that all of your distributions are continuous, right? Because if you have discrete contributions, you could easily set epsilon to 0.
Not really easily, because depending on how far the prior is from the likelihood, you can also, even if it's possible to have a mass different from 0 for exactly pseudo data equal to the observed, it will take a while to get equality. Okay. So even in that case, it's extremely difficult, and you have to wait too long.
So you would still need an epsilon, which is not 0.
Yes, sure. Even in the discrete case, you need an epsilon which is strictly greater than 0. Here, but let's see. In fact, there is no epsilon at the end. You will see. So okay, this is the ABC target. Here I have this very nice and standard toy example from Richard Wilkinson, who gave a very nice tutorial in NIPS in 2013. So look, you have a y given theta, and this is a likelihood. This is a Gaussian of dimension 1 with a cubic function for the mean and a quadratic function for the variances. You take a prior which is uniform for theta between -10 and 10. You observe y equal to 2, and you say, okay, the distance is the standard L1 distance. Why not? And look what happened. So here is a simulated theta, here is a simulated y. The red line corresponds to the observed y equal to 2, and the two dashed red line correspond to epsilon, the point you accept. And here you have the difference between the true and the ABC approximation, which is a kernel density estimator based on the accepted point within the bound here. And if epsilon is equal to 7.5, you have this approximation. If epsilon decreases to 5, you have this one right now. And if you continue to decrease the value of epsilon, the approximation comes closer to the true. Here, for epsilon equal to 1, you have an approximation which is very close to the true posterior distribution. So that's the point. Okay, in fact, practitioner does not use any epsilon before running the simulation and do this. They create what they call a reference table. So they simulate the value of theta using the prior, they simulate a pseudo observation using the model, and they calculate the distance. Then they order the distance here, and they return the value of the theta that correspond to the n smallest distance. Okay, so capital N correspond to a proportion of capital M simulation from the reference table. So you have simulated table here, and you have order according to the distance and take the smallest. This is the KNN approximation of the posterior expectation if you take the empirical expectation over this theta value. So this is just a K-nearest neighbor approximation, and epsilon corresponds to a quantile of the distance here. Okay? You get it. So epsilon is not fixed, is determined by the data you simulate, which is called the reference table. Okay, so this is emphasized in this paper of Gérard Viau and co-authors in Annales de l'IHP. This method is intuitive, simple to implement, embarrassingly parallelizable, but you have a curse of dimensionality. Most of the simulation are at the boundary of the space as the number of summary statistics increase. You know better than me, I think, what curse of dimensionality is. So you have typically this curse, and this is the reason why we summarize the data. Another point is that there is two views of this ABC approximation. The first one comes from Wilkinson in his paper. It shows that ABC is exact, but for a different model. If you add a noise to your model with a level of noise which is associated to the value of epsilon, you get as posterior distribution the ABC target. So it's an exact algorithm for a noisy version of your model. First interpretation. The second one, which is due to Bloom in the paper in JASA, emphasizes that ABC is a kernel smoothing approximation of the likelihood function. Look, you have this here, coming, this is the ABC target, this is a rectangular standard kernel, and you can modify this rectangular kernel by introducing another kernel with a window which can be called epsilon or some other. And in fact, look, the prior distribution can be put outside of the integral, and you have this integral which corresponds to a kernel approximation of the likelihood. You take the product of the likelihood by a kernel and you integrate. So this suggests to modify the ABC algorithm, and instead of using a rectangular kernel, you can use some other sort of kernel, exponential, Gaussian, Epanechnikov, or what you want. So this view of ABC and this one allows to introduce some other ABC algorithm. Okay, you have also a lot of work on more efficient algorithm. Simulated all the particles from the prior distribution is very inefficient, And there is various sequential Monte Carlo algorithms that had been constructed as an alternative, and there is a lot of work, including some we developed with Marc Beaumont and Pierre Pudlot, Mohamed Sedki, and Christian and Ozer and Jean-Marie. And the key idea is to decompose the difficult problem of sampling from this target ABC when epsilon is small, it's very difficult to sample from this, into a series of simpler subproblems. At time 0, you sample from this distribution with a large value of epsilon, and then you use this approximation corresponding to this large epsilon as prior for the next step, and you decrease the value of epsilon. This is a sequential Monte Carlo idea, and it can work quite well, but as I will explain later, it's extremely difficult to calibrate. So, let's see. You have also, due to Majoram and co-authors in NAS, likelihood-free MCMC version of the sampler, which correspond to also a pseudo marginal MCMC things. Okay, this is completely associated to pseudo marginal MCMC, where there is a plugging of an unbased estimator in some sense of the likelihood, and when you take this ratio, you are exact in some sense for an augmented space. Okay. Something which is done a lot also in ABC paradigm is some regression adjustment and machine learning arrive. Beaumont in genetics proposed to, and co-authors, and with Balding and Zhang, it's a very clever paper, to use local regression adjustment of the parameter value. So they take a large value of epsilon and then they adjust this value of epsilon using a model. Okay, a model which is local linear. And they modify the value of epsilon according to this model. So this is a way to taking into account the weight and introducing a sort of non-parametric estimator, local non-parametric estimator of the posterior expectation. And Bloom and co-authors with Olivier François extend this result in statistics and computing in 2010 with heteroscedastic model and feed-forward neural networks to avoid the linearity assumption of the local linear regression adjustment of Beaumont. There is also a lot of work on the selection of summary statistics. There is 3 types of selection you can do. The selection of summary statistics is a crucial step. The summary statistics should not be in a very large dimension, but should have information about the parameter we would like to estimate here. So there is a best subset selection method, which are based on criteria like tau sufficiency or entropy. There is some projection method, the semi-automatic ABC method of Fernand and Prangel in GRSSB, which is a discussion paper. And you have also some regression techniques, read regression for Bloom and co-authors, and Lasso for Emma Saulnier and co-authors here. So, some different way to select or to weight the summary statistics using standard statistical things for the regularization, using a nice idea in projection, but which is very difficult to do in practice, let's say, this one. The idea of this one is to say, okay, the best way to summarize, if you would like to estimate the posterior expectation, is the posterior expectation itself. Okay, so that's clear. So do a first ABC approximation, and then use this first ABC approximation as a projection of your simulated dataset. Okay, but this is based on the fact that the first ABC approximation works well. Instead of that, it does not work quite well. And if the first ABC approximation works well, you don't need all this machinery. Suppose that the problem is resolved, the problem is resolved. So it's not in practice so doable. You have also some possibility to do some model choice within this paradigm, and this is the same. So we are in the Bayesian paradigm, so we probabilize the model space, so you have a prior distribution in the model space. So you simulate a model index using the prior, you simulate a corresponding parameter using prior, which is not now indexed by a model, and you simulate a data set according to the likelihood which corresponds to the model you just simulate when you choose a model here. And you calculate the distance, you order the distance, so you have a summarization here, and this summarization should have some information with respect to the model choice problem, not to the parameter inference. And you order the distance and you return the n smallest index, and then you can take a majority rule here within the index to select the model. So we are in a classification problem. You create your own table where you have model index and summary statistics, and you apply a k-nearest neighbor approximation to estimate the model post-error probability and to select a model. That's the point. Once again, a k-nearest neighbor approximation. So it can work pretty well if eta y is a sufficient statistics for the model choice problem. It's quite difficult to have a sufficiency condition on the model and not on the parameter. Okay, so in practice it's not so easy to find statistic who have information to discriminate between model, and you can have some surprise here. So it can work quite well, but if not, we publish this paper in NAS to do a warning. Be careful, summarization have to be taken into account. You have to take care of the way you summarize your data. It's not easy to have a summarization of your data that have some information to discriminate between model. And at the end, in this Series B paper in GRSS here, we give some sufficient condition for which this is not exactly in the ABC paradigm. We give condition for which the post-error probability converge to the best model in terms of the Kullback-Lebeau divergence. So also if the true model is not in the set of model, when you condition on a summary statistic which is not sufficient for the model index. So we have some condition, and we apply this condition to our typical population genetic example, and you are able to see that it can work. Okay, so there is some year of controversy to use or not ABC to select a model, but okay, at the end we have these positive results. Here, you can use a not sufficient summary to discriminate between model, and if you have a lot of data set, we have a theorem that it can still work. You are able to recover the true model. Okay. So we have also investigated some ABC model choice techniques that use other machine learning procedures than the k-nearest neighbor, and this is the first step to use machine learning within the ABC paradigm. Here, this one. There is a lot of software right now which implements the method. This is a set of R package, including ours, which is ABC using random forest here. And there is also some specific tools we are associated to specific class of model. With this R package, you need to have your own simulation. So you have your reference table, and you give the reference table to the package to get the ABC approximation. Within this one, you have also some simulator included, and we have developed this do-it-yourself ABC software which perform estimation and model selection for a large class of population genetics model which are based essentially structured coalescent model here. So we have these two contributions, and so we apply this ABC technology on Asian ladybug, European honeybee, Drosophila suzuki, to pygmies population, and also to some study on 4 human population to study the out of Africa colonization here. So we applied on different type of data sets. So we have a DNA data set, and we would like to recover the population structure using DNA observed at the present time. Okay, and we would like to recover the population history. That's the goal of this. Okay, let me give some frontline news from population geneticist country, and I can do that because we have a lot of return from molecular ecologists which use the Hawaii ABC. The second version of the Hawaii ABC has been published in 2014 and has now around 300 citations, so we have a lot of feedback and how it works and who works, who are not working well. Simulate from the model can be very computationally intensive, and so parallelized algorithms are necessary. Okay, that's the first point. For this class of population genetics model, you need to design an algorithm which can use parallelization in an easy way. Okay, that's the first thing. The second one is likelihood is intractable due to the strong and complex dependent structure of the model. Okay, and that's a crucial point. If you have some ID data, I think, not in all cases, but in general, you can find better approximations than using approximate Bayesian computation. Okay, so use approximate Bayesian computation when the data set you observed has a very complex structure, and you would like to recover this complex structure. For ID data, you have some other set of approximation, and for sure, the variational and Laplace things can do a good job in that context. Okay. Sequential methods are very difficult to calibrate and do not give reproducible results. We found that with my PhD, Mohamed Sedki, and we worked hard, but we are not able to find a way to use this sequential method and to calibrate, and that the calibration are not too data dependent. Okay, that's a problem. Here I see a lot of data-dependent calibration in deep learning, so we try to avoid that. Okay, not to turn button for 6 months to get the results, and that's a problem with this sequential method. Postdoc and judgment are crucial, but they underestimate the amount of uncertainty. That's typically what we observe. And available techniques to select the summary statistics does not give also reproducible results. So it's a big challenge here. So despite all this work, there is two major difficulties. The first one is that to ensure reliability of the method, the number of simulations should be large, and the choice of the summary statistic is still a problem. Okay, that's the two typical points. And okay, we say avoid the can-nearest neighbor approximation and try to use more modern and clever machine learning tools on this table. That's what we would like to do, and that's what we have done, and also Kai and so some other have done that. I will show you. Exploiting a large number of summary statistics is not an issue for some machine learning method, and our idea is to learn on a huge reference table using random forest. I will explain why random forest in some sense. In some time, the first is that there is some theoretical guarantee for sparse problem. There is these two nice papers from Gerard Bio and co-authors, one in GMLR, one in the Annals of Statistics, who show some nice convergence results for sparse problem, and we are typically for my population genetic application in sparse problem. We have a big set of summary statistics, and within this big set, only few are related to the problem, and you want to pick up in this big step some guys which are related to the problem and also correlated. Okay, and the forest can do that. This works then at the interface between Bayesian inference and machine learning technique, and there is also some alternative. You have the alternative of Papamacarius and Murray, who propose to using mixture density network of Bishop in this paper in NIPS 1 year ago. Okay, here. And the mixture density network strategy consists in using Gaussian mixture model with parameter calibrated thanks to neural networks. And the idea is to iteratively learn an efficient proposal prior, that's an interesting point, approximating the posterior distribution, and then use this proposal to train the posterior. So in some sense, you localize by learning a prior with a network, and then you connect, it's a sort of autoencoder of things. And then you connect this prior to train the posterior using also a mixture density network. Okay, there is two difficulties associated with this method, that the number of mixture components and the number of hidden layers of the network require a lot of calibration. And once again, it's very problem specific to specify these two quantities, as we observe, but I think works have to be done to give rule to calibrate these two quantities, and this method can be very competitive for the ABC. There is also this paper which is specific to population genetics inference and to a specific class of coalescent process, which is by Sheham and Yoon-Sung. Yoon-Sung is a well-known guy in the population genetics community. They published a paper in PLOS Computational Biology 1 year ago, and they use deep learning, use a multi-layer neural networks to learn a feature-based function from the output. The input is the correlated summary statistic to the output, which are the population genetics parameter of interest. I think that the unsupervised pre-training using autoencoder is very interesting, but require a lot of calibration too. And there is also some alternative outside the population genetics community by Karl Kramer here, who have done, in some sense, some sort which is very close to this here. Okay, so our proposal is to use random forest because we found that random forest does not need calibration in some sense. We use a parameter proposed by Breman in this seminal work, and this set of parameters are quite good for a very large class of problems, and this is the reason why, to avoid fine-tuning, we choose the forest here. And so we published this paper for model choice in bioinformatics 1 year ago. So the input is a reference table involving the model index. So you have the model index and the summary statistics, and this is your learning set. So you have simulated your learning set. And the summary statistics are a large collection from scientific theory input to machine learning alternative. You use linear discriminant axis as summary statistics. We use the SVM classifier as summary statistics, a logistic regression classifier also. So we put all we can in the summary here. And then this is generated from this reference table where we get the model index and the summary. Okay? And the output is a random forest to infer the model index. Because to select a model is a classification problem, you have to affect the observed data to a class. A class is a model. And to do that, we simulate your learning set using the Bayesian model, using the prior and the likelihood. And then you learn on the table you have simulated. It's extremely simple. 45 minutes, it's too much perhaps to say something like that. But it's very simple, okay? You can predict the model index. Predict the model index is a classification problem, but estimate in a good way the posterior probability is a regression problem. This is the expectation of an indicator function, which is probability. This is a regression and not a classification problem. Regression is more difficult than classification in some sense, and you cannot directly use the result of the forest. The frequency of tree associated with the majority model is not a proper substitute to the true posterior probability. okay, of the selected model. So we will do something else to estimate this posterior probability here, okay, because the forest has been calibrated to do a classification job and not a regression job. The forest is to classify, not to estimate the probability. Okay, the criteria for each node of the forest is the Gini index or the entropy. It's not associated to any regression criteria. So this forest is not good to use to estimate. You can do that, but it's not good. So you have an alternative. Look at that. This is a selected model using, this is the probability of the selected given the data, and the random come from M. Wrong. M. I do a Bayesian research today, so the random from M. M is Bayesian. I condition on my simulated dataset, my reference table, and I condition on the observed. All the random come from M here, okay, in this equation. So you have this, extremely simple, and then if you are able to estimate this, you are able to estimate this guy. And so we will construct the forest to estimate this expectation, and this is not a classification random forest, but a regression random forest to estimate this expectation. So you compute the value of this here, using the out-of-bag classifier to avoid overfitting here, and to use the same reference table for the two forests, and you train a forest to estimate this, and this is a regression forest on the 0, 1. So this is a 0, 1. You have got the good model or not, and you train a second forest to estimate this, and you get the estimate of the posterior probability of the selected model, and you use the same reference table because of the out-of-bag magic trick to avoid overfitting. Here I have used the out-of-bag classifier to decide if this is 0 or 1. Okay, we have exactly the same type of methodology for regression to estimate parameter. For parameter inference, I show you how to select a model using this, and we can do the same to estimate a parameter. So the input is a reference table, and in the reference table you have right now the parameter value and the summary statistics, and you will learn. So this is a simulation of the reference table. You simulate the parameter value from the prior, you simulate the pseudo-observed, you summarize, and you have in lines each simulation with corresponding parameter value and the column of the summarization. And the output is some regression random forest predictors, not only one, to infer posterior expectation, quantile variance, and covariances. I don't try to estimate the whole posterior. I will design a forest, a random forest, to estimate a specific quantity. If I am interested with posterior expectation, I construct, and that my parameter is in dimension d, I construct d regression random forest, one per dimension. If I would like to estimate some quantile in order to have some confidence interval or credible set, we say by an inference on the parameter, we use a quantile regression forest clever method of Menshausen, and you don't need to simulate new forests compared to the one who has been done to estimate the expectation, because using this one, Menshausen gives a very nice trick to estimate the cumulative distribution function, and you have just to inverse this cumulative distribution function, and you get all the quantile you need. For the posterior variance, there is no new forest compared to the posterior expectation, and you use a out-of-bag trick also. And for posterior covariances, you have to design a new forest for which the response variables are the product of out-of-bag errors. Okay? So for each parameter we would like to estimate, we design a machine learning strategy specifically for the considered problem. We don't try to approximate the whole posterior. We think it's too difficult. Okay, there is one problem we're interested right now on. We construct forests able to estimate everywhere in the space of summary statistics, but we are interested only in one point, the observed dataset. I am in a very specific case of learning. I produce my learning set using the Bayesian model, and I just want to predict one point, the observed. Okay, and using this forest, I construct a rule, which is a general rule, able to estimate everybody who come in the machine. So right now we try to construct local random forest, and this is the goal of my PhD thesis, which is called Bernard. And what we do is, within the construction of the tree of the forest, at one node, for instance, we take into account of the point we would like to estimate to decide the split of the node between the two children. Okay, this is binary tree with two children, and we have a local criteria here right now, but it's quite difficult. Okay, few minutes on ABC and PAC-Bayes. There is some work on Bayesian and PAC-Bayesian frameworks. These two frameworks are run from each other. There is this nice paper of Pascal, Francis, and co-authors 1 year ago, choosing the negative log likelihood as the log function gives that minimizing the PAC-Bayes bound is equivalent to minimizing the marginal likelihood, and this big and very interesting connection between the two techniques. I am not in the ABC paradigm, but I will say some words. There is also this paper in Series B, the paper of Chris Holmes and Walker and B series. They produced paper in 2012, I think, and the paper appears in 2016. So 4 years of review. So perhaps a lot of discussion with the PAC-Bayesian guys, but it's almost the same as the Bayesian view of the PAC-Bayesian paradigm, without an emphasizing on bounds and things like that. But this is exactly this, and there is this very nice methodology when we have a misclassification model, the safe Bayesian, safe from Peter, and Peter speak about that. So this gives big connection, and I think that this safe Bayesian is a good thing. In some sense, it's not far from ABC. So you modify your model when flat prior, the likelihood in some sense to get more weight to the prior. And by taking this epsilon in the ABC fashion, we do almost the same. If the model is wrong, we enlarge the possible value for the corresponding model by using this threshold epsilon. So there is right now some work of why ABC can be interesting for misclassification models too. Okay, so now ABC approximation are based on the existence and the use of the generative model. I have a generative model, and I use this generative model to simulate my learning set, my reference table. This is, in some sense, antithetical with the PAC-Bayes paradigm, where there is no explicit modelization of the observed dataset. First point. Second point, I don't think that ABC approximation is useful when the calculation of the likelihood is tractable. I think that if you are able to calculate the likelihood, there is more clever approximation than this approximation. So it's not a good idea, I think, to use ABC as an inferential tool for trying to get simulation from the PAC-Bayes pseudo-posterior. I hear this morning that there is not direct connection between the prior and the posterior in the PAC-Bayes. I really not understand this, because I see the PAC-Bayesian as a pseudo-likelihood in some sense, using a prior, and then there is a corresponding posterior. But I am a Bayesian and totally candid in this field. So, what I can say is, don't use ABC to try to approximate this PAC-Bayes pseudo-posterior. So, first conclusion, the ABC toolbox seems unable to bring anything to the Bayesian framework first. But, on the other hand, I try to convince you today that ABC concerns are machine learning concerns. Okay? So, why not trying to use back-biased learning on ABC reference table? That can be a good thing to do here. And contrary to the standard context, we have two specific things. I repeat, but teaching is repeating. We generate the learning set, and we are only interested to predict one point, the observed data set. And there is some connection perhaps and some possibility to use some back Bayesian methodology, especially designed for these things, and I see this transductive learning, and in some sense we would like to do a transductive learning for one point, okay? Perhaps it can be helpful, I don't know. Moreover, there is this very nice preprint from Ridgway who use and who studies the convergence of ABC posterior under model misspecification, and he used concentration inequalities. We see a lot of concentration inequalities this morning in some sense, and he used back Bayesian analysis, and this is he gets really interesting and clever results for what do ABC under misspecification, connected to what I say to Peter here, and to say if ABC can be good under misspecification using, in fact, back Bayesian analysis here. So I think this is the most interesting connection here. And to the end, so yesterday with Benjamin and Pascal in a Chinese restaurant, I got an hidden message within a cake. The message was, sorry, this year take comfort in your rituals, but be open to new experiences. So I think I should try to use some back Bayesian results. So thank you very much for your attention.
Thank you very much, Jean-Michel, for this nice talk on ABC and this nice message at the end, which is a hope for a lot of people who do not do back Bayesian and who should do back Bayesian, maybe. So we have time for questions. Comments? Yeah. And could you be repeating the question, Jean-Michel?
I will try.
Yeah, thank you for the talk. Can you comment on the connection with the frequentist indirect inference, which seems to be a similar approach?
Okay, so the question is about connection between ABC approximation and frequentist and direct inference. There is a lot of connection between these two things, but in some sense, in the frequentist and direct inference, there is a choice of a class of model in which the approximation belongs, and there is not this choice here. Okay, in the indirect frequentist and direct inference, in some sense, this is quickly say, but they choose a class of model in which the approximation belongs, and that is not the case here. But this is very related. This is highly related. They also use simulation to calibrate the approximation, so in some sense, and simulation from the likelihood. So that is in some sense that there is a lot of connection, but it's isolated, but not completely the same thing.
Okay, in the interest of time, we should move on to the next speaker. Let's thank Jean-Michel again.